In classical mechanics, a harmonic oscillator is a system that, when displaced from its equilibrium position, experiences a restoring force, F, proportional to the displacement, where K is a positive constant. If F is the only force acting on the system is called a simple harmonic oscillator, and it undergoes simple harmonic motion. Sinusoidal oscillations about the equilibrium point, with a constant amplitude and a constant frequency. If a frictional force proportional to the velocity is also present, the harmonic oscillator is described as a damped oscillator. Depending on the friction coefficient, the system can oscillate with a frequency lower than in the non-damped case, and an amplitude decreasing with time, decay to the equilibrium position, without oscillations. The boundary solution between an underdamped oscillator and an overdamped oscillator occurs at a particular value of the friction coefficient and is called critically damped, if an external time-dependent force is present. The harmonic oscillator is described as a driven oscillator. Mechanical examples include pendulums, masses connected to springs, and acoustical systems. Other analogous systems include electrical harmonic oscillators such as RLC circuits. The harmonic oscillator model is very important in physics, because any mass subject to a force in stable equilibrium acts as a harmonic oscillator for small vibrations. Harmonic oscillators occur widely in nature and are exploited in many man-made devices, such as clocks and radio circuits. They are the source of virtually all sinusoidal vibrations and waves. Simple harmonic oscillator. A simple harmonic oscillator is an oscillator that is neither driven nor damped. It consists of a mass m, which experiences a single force, F, which pulls the mass in the direction of the point x equals 0 and depends only on the mass's position x, and a constant K. Balance of forces for the system is solving this differential equation. We find that the motion is described by the function where the motion is periodic, repeating itself in a sinusoidal fashion with constant amplitude. In addition to its amplitude, the motion of a simple harmonic oscillator is characterized by its period t, the time for a single oscillation, or its frequency f equals 1, t, the number of cycles per unit time. The position at a given time t also depends on the phase, phi, which determines the starting point on the sine wave. The period and frequency are determined by the size of the mass m and the force constant k, while the amplitude and phase are determined by the starting position and velocity. The velocity and acceleration of a simple harmonic oscillator oscillate with the same frequency as the position but with shifted phases. The velocity is maximum for zero displacement, while the acceleration is in the opposite direction as the displacement. The potential energy stored in a simple harmonic oscillator at position x is damped harmonic oscillator. In real oscillators, friction, or damping, slows the motion of the system. Due to frictional force, the velocity decreases in proportion to the acting frictional force. While simple harmonic motion oscillates with only the restoring force acting on the system, damped harmonic motion experiences friction. In many vibrating systems, the frictional force Ff can be modeled as being proportional to the velocity v of the object. Ff equals minus cv, where c is called the viscous damping coefficient. Balance of forces for damped harmonic oscillators is then when no external forces are present. This can be rewritten into the form where is called the undamped angular frequency of the oscillator, and is called the damping ratio. The value of the damping ratio zeta critically determines the behavior of the system. A damped harmonic oscillator can be overdamped. The system returns to steady state without oscillating. Larger values of the damping ratio zeta return to equilibrium slower. Critically damped. The system returns to steady state as quickly as possible without oscillating. This is often desired for the damping of systems such as doors. Underdamped. The system oscillates with the amplitude gradually decreasing to zero. The angular frequency of the underdamped harmonic oscillator is given by the exponential decay of the underdamped harmonic oscillator is given by the Q factor of a damped oscillator is defined as Q is related to the damping ratio by the equation driven harmonic oscillators. Driven harmonic oscillators are damped oscillators further affected by an externally applied force F. Newton's second law takes the form. It is usually rewritten into the form. This equation can be solved exactly for any driving force, using the solutions Z which satisfy the unforced equation, and which can be expressed as damped sinusoidal oscillations, in the case where zeta 1, the amplitude A and phase phi determine the behavior needed to match the initial conditions. Step input in the case zeta less than 1 and a unit step input with x equals 0. The solution is, with phase phi given by the time an oscillator needs to adapt to changed external conditions, is of the order tau equals 1. In physics, the adaptation is called relaxation, and tau is called the relaxation time. In electrical engineering, a multiple of tau is called the settling time, i.e., the time necessary to ensure the signal is within a fixed departure from final value, typically within 10%. The term overshoot refers to the extent the maximum response exceeds final value, and undershoot refers to the extent the response falls below final value for times following the maximum response. Sinusoidal driving force. In the case of a sinusoidal driving force, where is the driving amplitude and is the driving frequency for a sinusoidal driving mechanism. This type of system appears in AC-driven RLC circuits and driven spring systems having internal mechanical resistance or external air resistance. The general solution is a sum of a transient solution that depends on initial conditions, and a steady state that is independent of initial conditions and depends only on the driving amplitude, driving frequency, undamped angular frequency, and the damping ratio. The steady-state solution is proportional to the driving force with an induced phase change of, whereas the absolute value of the impedance or linear response function in is the phase of the oscillation relative to the driving force. If the arctan value is taken to be between -180 degrees and 0, for a particular driving frequency called the resonance, or resonant frequency, the amplitude is maximum. This resonance effect only occurs when, i.e., for significantly underdamped systems. For strongly underdamped systems, the value of the amplitude can become quite large near the resonance frequency. The transient solutions are the same as the unforce being applied by changing the moment of inertia of the swing by rocking back and forth or alternately standing and squatting, in rhythm with the swing's oscillations. The varying of the parameters drives the system. Examples of parameters that may be varied are its resonance frequency and damping. Parametric oscillators are used in many applications. The classical varactor parametric oscillator oscillates when the diode's capacitance is varied periodically. The circuit that varies the diode's capacitance is called the pump or driver. In microwave electronics, waveguide, YAG-based parametric oscillators operate in the same fashion. The designer varies a parameter periodically to induce oscillations. Parametric oscillators have been developed as low-noise amplifiers, especially in the radio and microwave frequency range. Thermal noise is minimal, since a reactance is varied. Another common use is frequency conversion, e.g., conversion from audio to radio frequencies. For example, the optical parametric oscillator converts an input laser wave into two output waves of lower frequency equals cos equals cos equals cos, where omega equals omega tc. The equation becomes the solution to this differential equation contains two parts, the transient and the steady state. Transient solution. The solution based on solving the ordinary differential equation is for arbitrary constants C1 and C2. The transient solution is independent of the forcing function. Steady-state solution. Apply the complex variables method by solving the auxiliary equation below and then finding the real part of its solution. Supposing the solution is of the form its derivatives from 0 to second order, substituting these quantities into the differential equation gives. Dividing by the exponential term on the left results in equating the real and imaginary parts, results in two independent equations. Amplitude part. Squaring both equations and adding them together gives therefore. Compare this result with the theory section on resonance, as well as the magnitude part of the RLC circuit. This amplitude function is particularly important in the analysis and understanding of the frequency response of second-order systems. Phase part. To solve for phi, divide both equations to get this phase function is particularly important in the analysis and understanding of the frequency responsive second-order systems. Full solution. Combining the amplitude and phase portions results in the steady-state solution. The solution of original universal oscillator equation is a superposition of the transient and steady-state solutions. For a more complete description of how to solve the above equation, see linearoids with constant coefficients. Equivalent systems. Harmonic oscillators occurring in a number of areas of engineering are equivalent in the sense that their mathematical models are identical. Below is a table showing analogous quantities in 4 harmonic oscillator systems in mechanics and electronics. If analogous parameters on the same line in the table are given numerically equal values, the behavior of the oscillators, their output waveform, resonant frequency, damping factor, etc., are the same. Application to a conservative force. The problem of the simple harmonic oscillator occurs frequently in physics, because a mass at equilibrium under the influence of any conservative force, in the limit of small motions, behaves as a simple harmonic oscillator. A conservative force is one that has a potential energy function. The potential energy function of a harmonic oscillator is given an arbitrary potential energy function. One can do a Taylor expansion in terms of around an energy minimum is arbitrary and thus may be dropped. And a coordinate transformation allows the form of the simple harmonic oscillator to be retrieved. Thus, given an arbitrary potential energy function with a non-vanishing second derivative, one can use the solution to the simple harmonic oscillator to provide an approximate solution for small perturbations around the equilibrium point. Examples. Simple pendulum assuming no damping. The differential equation governing a simple pendulum is if the maximum displacement of the pendulum is small. We can use the approximation and instead consider the equation. The solution to this equation is given by where is the largest angle attained by the pendulum. The period, the time for one complete oscillation, is given by the expression which is a good approximation of the actual period one is small. Pendulum swinging over turntable. Simple harmonic motion can in some cases be considered to be the one-dimensional projection of two-dimensional circular motion. Consider a long pendulum swinging over the turntable of a record player. On the edge of the turntable there is an object. If the object is viewed from the same level as the turntable, a projection of the motion of the object seems to be moving backwards and forwards on a straight line orthogonal to the view direction. Sinusoidally, like the pendulum. Spring mass system. When a spring is stretched or compressed by a mass, the spring develops a restoring force. Hooke's law gives the relationship of the force exerted by the spring when the spring is compressed or stretched a certain length, where F is the force, K is the spring constant, and X is the displacement of the mass with respect to the equilibrium position. The minus sign in the equation indicates that the force exerted by the spring always acts in a direction that is opposite to the displacement, and so prevents the mass from flying off to infinity. By using either force balance or an energy method, it can be readily shown that the motion of this system is given by the following differential equation, the latter being Newton's second law of motion. If the initial displacement is a and there is no initial velocity, the solution of this equation is given by, given an ideal massless spring, is the mass on the end of the spring. If the spring itself has mass, its effective mass must be included in energy variation in the spring damping system. In terms of energy, all systems have two types of energy: potential energy and kinetic energy. When a spring is stretched or compressed, it stores elastic potential energy, which then is transferred into kinetic energy. The potential energy within a spring is determined by the equation. When the spring is stretched or compressed, kinetic energy of the mass gets converted into potential energy of the spring. By conservation of energy, assuming the datum is defined at the equilibrium position, when the spring reaches its maximum potential energy, the kinetic energy of the mass is zero. When the spring is released, it tries to return to equilibrium, and all its potential energy converts to kinetic energy of the mass. Definition of terms.